those things are counter to each other, right? And so that's why these systems are called antagonistic systems, right? This is the same example of insulin and glucagon, right? They're opposing systems. And so we'll see how these systems oppose each other in a bit. But before we get there, I want to talk a little bit about homeostasis and how it's regulated. Now that you have a little bit more idea about what the nervous system's about, parts of the brain, what they do, it's good to kind of understand the pathways here. So, it starts with any kind of sensory input, whatever senses pick up, whether it's blood pressure, heart rate, ion levels, whatever it is, that information is going to be sent to the hypothalamus, or get picked up by hypothalamic sensors, or some other kind of sensors in the body. So somatic sensors could be like baroreceptors in your arteries. Well, actually, that's an example of visceral. Sorry. Somatic sensors could be like sensors that detect tension in your muscles, and visceral sensors can be sensors that are in your blood vessels detecting blood pressure or some other kind of variable. So this information either goes to your pons, your medulla oblongata, or your hypothalamus, or they go into something called the limbic system here. Or if you have conscious thought about it, it goes into your cerebral cortex. And so from there, it can create some different responses. So you can have an endocrine response. So we talked about how the hypothalamus can talk to the pituitary gland, and that's the hormonal response. We talked about that. But we can also have an autonomic response, where we send nervous impulses through the autonomic divisions, whether it's sympathetic, parasympathetic, to also create changes too. And so these are faster changes because they're traveling through neurons, right? And of course, what's put here is behavioral changes. So an example of a behavioral change is, for example, is your glucose levels are low, and then your brain will feel like, oh, I'm really tired, I should sit down, I should lie down, or I should even go to sleep. So that's an example of a behavioral response. It's not really a response that relates to a hormone per se, or relates to, muscles contracting or relaxing. This is more about you doing an actual behavior, whether it's sitting down, lying down, or you eating. Alright, so back to autonomic systems. All autonomic nervous systems essentially are just made out of two neurons. In that sense, it's really easy to think about. There's this preganglionic neuron, so it takes information from the central nervous system and brings it to this junction, which we'll call the autonomic ganglion. So hopefully from now you learn that a ganglion is basically a cluster of cell bodies outside the central nervous system. And so this is an example of one. And then at the autonomic ganglion, the preganglionic neuron will synapse to a postganglionic neuron. And hopefully that makes sense why they have the name preganglionic and postganglionic, before the ganglion and after the ganglion. That's kind of where they get their names, so it should be kind of intuitive. And so this postganglionic neuron will then take the information that was given by the preganglionic neuron, right? There's a whole synapse here, so there's a release of neurotransmitters that creates a graded potential in the postganglionic neuron. This is all this information, all this kind of excitation or inhibition we talked about last lecture. And then it will conduct that information to whatever the target tissue could be. So this can be various things. Most likely it's muscle. Sometimes it can be a gland. And in some situations it can be fat cells too. And so any autonomic pathway is going to be something like this. It's going to be just two neurons that travel starting at the central nervous system, some part of the spine or the brain, and then it's going to travel to whatever tissue it needs to affect, whether it's a muscle, fat, gland, whatever, and it only takes two neurons. So in that sense, it's kind of simple. But at this point, this is where you can start seeing differences between, just at this level, this is where you're going to start seeing differences between the parasympathetic system and the sympathetic system. So here we have the sympathetic pathway here. Let me just change the highlighter. Sympathetic pathway right here. And so here our preganglionic neuron is releasing acetylcholine here. So at the autonomic ganglion, acetylcholine is being released as a neurotransmitter. Hopefully you remember that from last lecture. I told you that that's one of the neurotransmitters you gotta know about. And it turns out the parasympathetic pathway, their preganglionic neurons also release acetylcholine. And the receptor that receives the acetylcholine are nicotinic receptors. So hopefully you remember nicotinic receptors. Why do you think nicotinic receptors are called nicotinic? We talked about that. Because nicotine, let me write it down. Nicotine is what we call is an agonist, right? It means it can excite these, it can bind and activate these nicotinic receptors as if they were like acetylcholine. That's why we call them agonists, right? And where do you normally find nicotine day-to-day life? Cigarettes, right? So you can think about when you smoke a cigarette and you get nicotine in your blood, you're going to be affecting your autonomic nervous system, right? You can not only have sympathetic effects, but you can also have parasympathetic effects. That's why you ever talk to a smoker, you'll get different responses about how they say smoking affects them. Sometimes they'll say it relaxes them. Sometimes it tells them it sharpens their, their clarity, and that's because nicotine has both these sympathetic and parasympathetic effects. It can also release adrenaline, epinephrine, make you a little shaky, but in some people it can kind of give this relaxing effect. And so, it's, in medical literature, it's called like, I believe, Nicotil's paradox. Nicotil was I think the doctor who discovered this paradox. But this is to the point. Nicotine can also affect your autonomic pathway. But at the postganglionic neuron, this is where we see differences between the sympathetic and parasympathetic pathways, as when they release neurotransmitters to affect the target tissue, it's different. For the sympathetic pathways, it's norepinephrine, right? And they have this adrenergic receptors, right? They call adrenergic because they're affected by adrenaline, which norepinephrine and epinephrine are. But the parasympathetic pathways will still continue to release acetylcholine, and they have a different type of receptor. They have muscarinic receptors. I always have a hard time saying that. And those are special agents that are derived from some kind of mushroom. And so at just a 2-neuron level here, we're already seeing differences between the parasympathetic nervous system and the sympathetic nervous system here. Right? What neurotransmitters to use at what neurons. Now here is kind of the autonomic system in all its glory. Now it looks like a lot, but remember all of these pathways here are just 2 neurons put together in series. So just remember that. It shouldn't be too bad. But what this graph is showing you here is all the places that the sympathetic and the parasympathetic nervous system kind of affect via their neurons. So the sympathetic neuron here shown in red to elicit this kind of visceral response, this kind of heightened response. When you think about red, you think about kind of blood, kind of heightened levels. So here we can see we have branches to the heart, to the lungs, to the urinary bladder, and then for the parasympathetic system, we see a blue color, calming color. We see it also kind of links up to a lot of same places: the heart, the urinary bladder, the lungs. All these places are still kind of having inputs from the sympathetic system and the parasympathetic system. And so this table right here is showing you kind of the responses that the parasympathetic system and the sympathetic system will have on a given organ. And these should hopefully make sense to you, kind of given their effect. Because think about what the jobs are, right? The sympathetic system is supposed to, put you in this fight or flight state, while the parasympathetic system is trying to relax you, trying to make you conserve energy, right? So if you look at the heart here, right, the sympathetic response is to increase heart rate and the force of contraction. That makes sense, right? You have to exercise, right? So you need that heart rate to increase. You need force that contraction to increase that blood pressure. But then the parasympathetic response here is just to slow the heart rate, right? And so the sympathetic is going to increase the heart rate, while the parasympathetic is going to decrease the heart rate. And so these are antagonistic controls. Remember, we talked about that. We talked about chapter 6 about antagonistic control. Well, here's an example of it, right? One neuron is telling the heart to do something else, while the other postganglionic neuron is telling the heart to do something else, and which one will win out is the one that's going to have a stronger signal, aka it's going to have a higher frequency of action potentials. So try to hopefully connect this information from previous lectures. And so that's an example of antagonistic control, but there's another example here of tonic control. So let's look at the kidney here. So this pathway right here, it's going to the kidney, and at the kidney, do I have it on the table here? I do not. You can read it right here. It's kind of small. It is going to increase secretion of the kidney. So you're going to basically, add more urine to the bladder. But notice here, there is no parasympathetic effect here. You'll also see that in blood vessels. I don't know if they show that here. Probably not. But blood vessels only have a sympathetic system input. They don't have a parasympathetic input. So that's not antagonistic control, because there's not two opposing neurons telling it to do different things. There's only one neuron telling it to do. And in that situation, you'll have tonic control. So its response is going to be related directly to the frequency of that neuron's action potentials. Is the frequency high? It's going to have a stronger signal. If its frequency is low, it's going to have a lower strength signal. And so this is how this parasympathetic and sympathetic system is going to work in tandem, right? Either one's going to be stronger, or the one's not, and it'll win over the other system, or the other one is just in charge of controlling certain organs, like the kidneys or the blood vessels. And so you should